research in pattern recognition, so to say, and machine learning, quantum information, and these disciplines has sparked fresh ideas for core problems across different areas: logic, engineering, computer science, philosophy, and so on. And uh, sorry, this investigation point back to, I would say, a venerable epistemological problem, a very old problem. How are abstract concepts formed, recognized, and classified from prior experience? This is a very old problem. So this is a question that is studied with different methods, both in human and artificial intelligence. And as is well known, the nature of concept and also the constraints that govern former theory of concept have been and continue to be the subject of much debate after more than 2000 years. An interesting position is the position held by Gestalt theorists. I think this is a particular illuminated quotation by Max Wertheimer, the founding father of the Gestalt theory. There are relations in which what happens in the whole does not derive from the individual parts and how they are combined, but rather the opposite, where in the most striking case, what happens to a part of this whole is determined by the internal structural laws of this whole. Strukturgesetze. This is the original German. And this raises, for example, it raises challenging data science, because part-based reduction that usually used in data science often lose crucial relational structure, relational structures. So complex systems, for example, require model that capture the global organizations, the phenomena. And quantum theory offers tools, particular good tools to model global structure that cannot be reduced to the single part of a phenomena. But before tackling the problem, which disciplines and tools do we need for attack this problem of concerning concept? Who studies classifications of objects apart philosophers, of course? Signals, events, objects in general. How do we frame quantum computation information for classification? So this is the aim of my lectures, to make explicit this connection explicit, as we will see here. So we have two parts. From one side, we have machine learners, as we learned from Rudy. I use his definition he gave. What is machine learning? Machine learning in general can be considered an art science, as the great Newt, the founding father of La Tech or Tech, says, is a science and art. Is a science and art of making computers learn from data to solve problems or recognize new unseen objects without being explicitly programmed. That's the point. On the other side, we have quantum computer. And we know that quantum computation describes information processing that are governed by quantum mechanics, using qubits. I thank again Klaus for the introduction this morning, so I don't need to repeat the notion of qubit, superposition, interference, and entanglement. Everything was introduced this morning. But the point is, why and how should we combine these two disciplines? This is the core questions of the lecture. So in the first lecture, we will take why the motivation from data science, technology, and quantum computation. What I call usually the reason of a happy marriage, between quantum information and data science. And how can conceptual bridges between and technical tools between the two sides. So I will introduce some very basic notions of usual classical supervised machine learning, lecture 1. Then we will see how to move towards the quantum world by means of the quantum encoding of classical data. How we encode classical data into quantum object. Then in the lecture tomorrow afternoon, we will see a particular example of a quantum classifier. And in the last part, if the quantum computer of the Leibniz Recon Center works, and this is, then we will see how can implement this quantum classifier into a real quantum device that is hosted here in our beautiful, that we have visited 3 days ago. So, over the last decades, no, I have access. I have full access to the computers, yes, so far. If I don't destroy them, I have access. Over the yes, thank you. Please don't take any picture when I project the symbols or the tokens of the computers of Library Training Center, because please don't do it, because so I should hide the token. I will hide the token because otherwise I cannot. Mhm. And so over the last decades, thank you, Stefania, in quantum information computer science, attracting really growing interest both in the computer science and theoretical computer science, applied computer science, and data science community. Because let me say, driven by potential for new paradigms of learning, optimizations, and information processes, machine learning, quantum computation, and here in the intersection, we see quantum machine learning. And why the quantum and data science should marry, so to say. First of all, from the classical point of view, we are faced with a dramatic increase in the amount of data. You see, exponential growing the amount of data. And especially the blue one are the unstructured data. That's the point. These are data that are without any meta assigned. So these are completely unstructured. And so then unstructured data is every data that don't have any key and any link, so completely without any reference to something other than the text itself. Okay. So the accumulation of data, the simple accumulation of data, does not necessarily equate to an accumulation of information. Now, this is well known. So a large data set may potentially hold significant information, but extracting that information is far from being straightforward. So then, large and more complex data set increase the computational cost of what? Of extracting patterns and correlations, structuring data, classifying and clustering unsupervised data, high-dimensional data, running large-scale simulation and optimizations, as we discussed also with Sturzen. So classical algorithms, often faced with time complexity barriers, scaling becomes exponential, and resource constraints. That's a very crucial point. Memory and especially energy usage explode, as we know from the example of large language models. So to go further, we need a fundamentally new computational paradigms. That's the point. So on the other part, we have a possibility, theoretical possibility, quantum computation, to speed up the process. This is what is promised. And we know the very well-known Shor algorithm that it was invented by Shor in 1994. This is the quantum circuit of the Shor algorithm. And the Shor algorithm provides an exponential speed up for integer factorizations compared to the best known classical algorithm. As philosophers, we have to be very careful. There is no Go theorem. There is no theorem say that there is no classical algorithm that runs in a polynomial type for the factorizations of integer. It's just a conjecture. This is the reason why we use our credit card, because we trust this conjecture. Because, as is well known, the factorization problem is strictly the solution of this problem implies that the usual RSA crypto method that we use in credit card cannot be solved in a time I would say less than the life of the universe. So we are very happy when we use our credit card because, okay, but there is a conjecture that the integer factorizing problem is not solvable in a polynomial time by classical computer. But Shor proved, on the contrary, that if we use quantum computers, quantum algorithm, we can factorize integer numbers in a polynomial time in an effective way, and therefore our credit cards at a risk. Because if we are able to solve the prime factor problem, we are able to crack our credit card. Okay? So, and this is based, as Professor Meitzer said this morning, the beautiful mathematics is based, the efficiency of this algorithm is based on the period finding problem for a specific modular function. Take a modular function here, fx equals to a power x modulus n. This is the problem is find the period. Find the period of this function. This is untractable from a classical point of view. And this is the base of the integer factorization. Shor proof that this problem can be solved in a polynomial time. So I will show now the package, a Python package with a circuit to solve this problem, the Shor problems. This is only based on a simulation because it's too expensive. So I will be immediately blocked by the Leibniz reconsent to the access if I try to use. But we will see a simulation of this. Let me see here. Okay. This is the Shor period finding. This is written as a language, as a quantum language in Qiskit. Qiskit is I think, the most popular language for quantum programming. Okay, it's very easy, but you can find. I will give you the reference. So first of all, I download everything. Now I define a function. You see here, the function f of x is equal to 13 power x modulus 15. The solution, the period of this function is 4, is 1, 4, 8, and so on. So we ask the computer the quantum computer to find the period. And find the period, I repeat, of a function, of a periodic function, is the key for factorizing integers. And therefore, so I try, let me see whether it works. I define the function, and now, this is the circuit. You see? This is introduced by Klaus this morning. And you see, this is the circuit to solve the period of a function. And you see you have not, because the x is not, and then you have the control not excluded all. Nothing more. What is crucial here, nothing more, you have in red, this is the quantum part of the circuit, Hadamard, as we see. The other classical gates can be simulated classical, but here Hadamard appears, and this is where quantumness enters into the play. So we try. Now, as you know, quantum computers, quantum mechanics is statistical. So now we have this circuit, which is initialized here. This is the input, okay? We run the circuit, but at the end, we have to measure. Because if we don't measure, we cannot extract any information from the circuit. That's the difference between quantum computation and classical computation. So, and how many? Usually 1,024. This is not a magic number. It's just the usual way. We repeat the experiments 1,024 times. Since the Leibniz Center are not so generous, sometimes we can use only 200 shots. But it doesn't depend on the Leibniz, but the Innsbruck factory. So we are blocked to 200 experiment. Now, what we expect is not an exact result, but a statistical result. So we will have at the end the solution are 1, the trivial solution, 4, 8, 12, because the period is 4. What they're interested essentially is 4, okay, because the period is 4. We run the machine, and you see here the result, the statistical result. This is, you see, 1, 4, 8, 12. And the probability should be exactly 0.25, 1 over 4, okay? 1 over 4 for every occurrence. But it's not so. You see here, this is 0.236, 0.262, and so on and so on. This is the best we can have with quantum computers, statistical results, but in a polynomial time. That's the point. So, come back to, I hope tomorrow to run a quantum circuit on the real, an actual quantum device, quantum machine. So Shor algorithms, in other words, is a benchmark example of how quantum mechanics can fundamentally reshape computational limits. From a purely theoretical point of view, because our near-term quantum computers are noisy, are unreliable, so we can be very sure that our credit cards are very safe, because they are not able to factorize large numbers. Okay. This is what is called, with a term that I do not like at all, quantum supremacy, because usually I hate the term supremacy in every possible meaning of the term. And what denotes what is called a point in which quantum computer performs a calculation that is unfeasible for any classical computer within a reasonable time frame. This is only an empirical conjecture There is no mathematical, it's not a mathematical conjecture. It's just only say that in a reasonable time frame. And there are examples. For example, you remember Google 6 years ago gave a very bold claim that they arrived at the quantum supremacy. It was published in Nature, and it was false, simply false, because after a few months, a classical and HPC computers had the same performance of the quantum computer. So we have to be very careful when we have these bold claims. I understand this big factory, but not but not scientists, genuine scientists. But there is a prototypical example of quantum supremacy based on physics, as is the so-called boson sampling, the sampling of bosons. And this can be after 3 years, 3 years, there is no classical example. There is an algorithm for boson sampling, photons, for example, that can run in 36 nanoseconds. And for the best actual HPC computers, needs 9,000 years of computation. This is the only, as far as I know, example, genuine example of quantum, what I call advantage, not supremacy. Then we have new-term quantum computers. This is IBM, this is Google Sycamore, and this is our beautiful that we saw 3 days ago. You remember this is the IQM, the superconducting computer that we use tomorrow. Please don't take pictures of materials covered by the Leibniz. And this is the AQT, and we didn't visit the AQT. This is the ion trap quantum computers, 20 qubits, which I like very much more than. And so, summing up, standard techniques for extracting useful information from large data sets are faced with strong computational bottlenecks. That is clear. Large language models, for example, require vast, huge computational resources with high energy usage and substantial carbon footprint. So, the conclusion is that the promised advantage of quantum computation is to drastically reduce time complexity and, as a consequence, energy consumption. So this is just a comparison of the tools we can use. You can take a picture of classical machine learning with Python. This is the package we use. And this is the package for quantum programming, the special Qiskit. Now there is also a quantum assembly program, which you can translate every dialect, so to say. And so it seems that the connection between machine learners and quantum computers is natural and in a certain sense, inevitable. But the problem is how these two different fields can be integrated. And this is the central question addressed by quantum machine learning, by the way. And currently there is a newborn disciplines. There is no widely agreed upon definition what quantum machine learning is. The quantum machine learning we use is called quantum-inspired machine learning. What does it mean? It means that we develop quantum native classifiers. So what does it mean, quantum native classifier? Usually in the quantum machine approach, they take classical algorithms, for example, support vector machine, neural networks, and so on, and then they use quantum mechanics, they quantize classical algorithms. And this happened in the history of quantum mechanics. Here, it's completely different. We start from classifier, from algorithms that are genuinely written by means of quantum formalism. They cannot be written with a classical language. That's the point. But they can be run also on classical computing. So far, and we hope, of course, that we will run also on quantum computer. So the point here, what we emphasize here is the classification accuracy rather than, yes, please.
So you said you can run the quantum algorithms on the classical computers. So is there a performance?
Yeah, we can, because again, you have the quantum algorithm is written in with a quantum formalism, okay, with a Hilbert space quantum mechanics. Then you translate your quantum algorithms into the language of a classical computer. Of course, it's not the ideal situation, but you can run, and you can see that also in this case, you have generally an increasing of the accuracy of the classification. Okay, we have to pay a price that is low. Sometimes it's low. We will see in a few minutes. So, of course, what we the aim of our research is to combine accuracy plus speed up. In other terms, running quantum algorithms on quantum devices in order to maximize accuracy and speed up. Okay, but just to give some elements, some real basic elements of classification. I'm sorry that is a bit boring for people coming for computer science, but maybe for philosophers not. A typical classification problem in supervised machine learning. What does it mean, supervised? Supervised machine learning, there is as machine learning that consists of a training part, something which is learned from data, and a test part where you, let me say, benchmark, you test whether you have learned from data. This is supervised. So we have a set of objects, and I use now the binary concept, okay? Positive, negative. We can extend also to n-ary. Then, for example, cats and dogs. We want to classify cats and dogs. So, as usual, also in physics, we select some relevant features, the head of the tail, and so on. Suppose, in our case, just 2 features. So, for example, and we will see an example, malignant or benign cells. This is another binary classification, which is quite critical. So, in the training part, we attach to every object. An object means a vector consisting of the numbers of the features. We attach a label: dog, cat, and so on. Features plus labels equals pattern. A pattern is a feature, a sequence of feature plus a label. So, what does it mean classifying? Classifying, you take any unlabeled object, any unseen object, and on the basis of what you have learned from the training data set, you classify this object as positive, negative, cat or dog, and so on. So the task of supervised machine learning is to infer, to tune a function, a classifier, from a given training data set of a classification domain that assigns a label, is a function, from a vector space to the labels. Okay? Let us see more formally. No, not more formally, more pictorially. This is cats and dog, disjoint set, okay? And we choose the weight and height as features. So every object is a pairs in the Cartesian plane. Weight, the number weight, and the number height. Okay, this is then we attach to X a label, dogs or cats, D or C, and we have the pattern. So this is the pattern. The pairs, weight, two numbers, and the label identifying the object. This is called the training data set. For example, cats and dogs. You see, the blue are dogs, and the red are cats. This is not very interesting because they are almost linearly separated. But usually they are not so. It's not so easy. Okay, because we are points red that are here. Take a very small cat, a very small dog, a very big cat. Okay. So the weight and height. Then we create a test data set. Test means a set of objects unlabeled, having empty intersection with the tree in order to avoid biases, leaking the classification. Then we apply the classifier to the object of the test, and then we calculate the accuracy of the classification. Exactly what happens with an exam at university. You learn something, and you test the training data set. Then you have the test, and you see the accuracy is your score, usually. So, more formally, we have an object is a d-dimensional vector in a real or complex space. Then we have a set of labels, okay, M labels. And we have the set of all the training data set here. The test data set intersection is empty. And at the end, we test the accuracy. So this is the binary case, you see, plus the positive label minus the negative label. And what is now a classifier from a formal point of view? Is nothing but a function taken as an argument vectors in the appropriate vector space as an output, the label, attribute a label. But how to define a classifier? What is the logic that underlying the classification? Let's see, very simple example, the so-called nearest mean classifier. This is so easy and so powerful. What does it mean? What is the nearest centroid classifier? Just from an intuitive point of view, you have two classes, positive and negative. These are vectors. Take the centroid, the positive centroid, and the negative centroid. These two elements represent the prototypical cat and the prototypical dog. Then how do you classify a new object? You take the distance. Of the new object between the distance of this new object between the centroid, the two centroid, and you decide. And you classify the new object as plus if it is closer to the centroid plus. It's very, very easy. Euclidean distance or any other possible distance. So here, this is the prototypical dog, the centroid. This is a prototypical cat, and not existent is a nominal, so to say. It's not a real object. It's a representative of the object. So now we test the classifier. Yeah, this is the test. We calculate for any possible unseen object the distance between the two centroid, and we have, sorry, see here. So how do we classify the function here? The classifier, this is an unknown object, okay? X is classified as plus if the distance of x with respect to the plus centroid is less than or equal to the distance between x and the centroid minus. And this is, and then you have the usual figure of Mavis, statistical, true, positive, true. This is the diagonal is a true positive, true negative, false negative, and false positive. This is called the confusion matrix. This is called confusion matrix. This is what is predicted. This is the actual value. So you have TP because what is predicted is exactly what is, and so on and so on. And the accuracy, of course, the accuracy of the classification is the sum of the diagonal elements, true positive plus false negative, over the set of all possible objects. Okay, so in this case, our classifier, the cat and dogs, is easy, you see, it's very easy, is 94%, a good classifier, I would say. In this case, but because the data set was very, very, very easy. And for example, in this case, the banana data set, which is very tricky, you see, the red here, then you have the blue here, the red, blue again, red again. So any linear classifiers at the nearest centroid doesn't work. You see, this is terrible. This is a terrible classification. But there are other classifiers, for example, here, you see here the neural network classifier is another classifier based on neural networks, is particularly performing. See, it is able to recover all of these tricky parts on this tricky part, and so this is the neural network. Okay, but the relation. Yeah, I'd like to show you an example, a practical example of a classical classifier with the nearest mean centroid, which is, you see, is very easy, with a classification of benign and malignant cell for malignant cell of melanoma. Okay, sorry, it's not very. I know it's an example, but we have very vivid images of. I will show you here how to classify. Here, I have to change. Sorry, the environment for the Python because I need another environment, another package for the Python, and so we need some minutes. I wrote also a sort of 2 or 3 pages if you are interested, for the students interested, to give all the details to install, to have this. Okay, it's a bit slow, so I proceed. We will see after. So now, from let me say, from a philosophical point of view, in the case of the nearest mean, the relationship that connects these ideal patterns with particular object can be expressed by using a similarity relation. That's the point. That the similarity relation is the key point in the classification, as you can imagine. The distance is the 1 minus, of course, the distance for the similarity. And so in classical pattern recognition, in the case of nearest mint, this is the typical workflow. Represent data in a suitable feature space, identify prototypes, centroids, classify new samples based on similarity to this prototype. So in the quantum-inspired approach, we will see, we keep this logical structure, the idea of similarity as founding, but not classical similarity, not any classical distance or similarity function, but quantum similarity function. We will introduce. So this shift opens the door to exploiting quantum mechanics, quantum properties in classification tasks, shifting from classical similarity function to quantum similarity function. But in order to apply similarity function, you need quantum object, not classical object. And so you need encoding. So you have classical data. We have to transform our cat and dogs into quantum dogs and cats, okay? In order to apply the similarity, quantum similarity function. So this is the workflow. Classical data, quantum encoding, transforming classical object into a quantum object, and finally classification. And so this is the transformation of our cat and dogs. You have a vector here, a cat, a dog, let me say. Then you transform this vector into a quantum object exactly in the quantum state that Professor Miles introduced this morning. That is a unit vector of a space. Okay? So you have the features, you transform it to a quantum object. But if you have a quantum object, you have a line, the line where the segment, the unit vector lies. But if you have a lines, you have a projection. You have an operator that projects onto the line determined by the unit vector. So what is at the end an encoding is a projection. It is the projection determined by the transformation of the encoding of the element into the object. So this is the usual notation in the Dirac notation. This is a projection operator. So you see classical object and then the quantum object. So and now you transform every classical object, so the training data set, the test data set, into their correspondence quantum object. How many ways are to encode a classical object into a quantum object? There are uncountably many ways to encode. So it's an open question. Now, in the one of the most important problems in quantum machine learning, try and find the optimal encoding that maximizes the accuracy of the classification. Maybe my conjecture is there is no optimal way, but it strongly depends on the nature of the data sets. So there is no universal, the best encoding. But so now, for example, we use, it's called the amplitude encoding, the stereographic encoding. It's not so important. It's just a transformation of the features in a quantum object. Yeah.
You can only the database or also on the quantum computer, which
That's a good question. You are right. There are at least two variables. Depend also on the particular quantum hardware you are running, because depending on the when you have an encoding, you have a theoretical results. I mean, from for the accuracy, but then you have to test on the quantum computers. And depending on the original encoding, if you use an ion trap quantum computer or a superconducting computer, you have different results, depending on the, yes, yeah, thank you. So, these are different, so this is, for example, let's see, this is the stereographic, this is the, the stereographic map. This is the inverse of the stereographic map. This is the called moon data sets. You have, which is not difficult. It's not linear, because this you see, but, okay, it's not difficult. And this is the how the object of the classical data set are transformed into quantum state. And these are exactly elements of the Bloch-Poincare sphere introduced this morning by Professor Mainzer. And these objects are pure states in quantum mechanics here, because are element of the surface of the Bloch-Poincare sphere. So now we have this transformation. Now we apply the machinery. We transform everything into quantum, so a quantum training data set. But the difference is here. Instead of taking the classical centroid, we take the sum of the projectors associated to the class. So in other terms, you have, let me see, this is very important, because this is the crucial distinction. Okay, so we have, let's say, cats and dogs. Then you have, let me see, xn, y, in. These are the classical vectors, okay? These are vectors. Then you take the encoding. The encoding, you have the projectors, okay? These are the quantum representative of the cats, and then similarly for them. Then the quantum analog of the centroid is the sum of this object. You take the object where sorry for the notation, where there are cats, and with nc, 1 over nc is the number of cats. This means that you have a sum of pure states that are weighted by the numbers of, and if you take this operator, this is called in quantum mechanics a mixture. This is a density operator, a sum of pure states weighted by the numbers of the elements. These are the quantum centroid. So this is a crucial difference, because a centroid is still an element of the real space. Here, in this case, a quantum centroid is no longer a pure state, a vector, but is an operator, is a density operator. So the quantum prototype is a mixture as density operators. So, go ahead a few minutes more. But, so this is the classification. Now, so far so good. The first step, okay, we have quantum cats, quantum dogs, the animal. But now, how can classify a new object? By means of a quantum similarity function. So we have to introduce a quantum similarity function. But the idea is quite similar. Instead of taking the similarity between the classical prototype, you will consider the quantum similarity between the quantum centroid and the embedded and the encoded object. But how? What is, I think, is beautiful here is that this is based on a profound physical property of quantum mechanics concerning the distinguishability, the discrimination of states. What does it mean? From a classical point of view, we will see tomorrow. This is the how to. So far we are able to encode classical object into quantum object, but we are not able to classify the object. We have the quantum counterparts of the objects, the vectors, the quantum counterpart of the centroid, but we don't have any quantum similarity function that allows us to classify an unseen object. So the idea I introduce here is the following. Take, for example, Alice and Bob, and if no Alice and Bob, no Alice and Bob, okay. Then I have this problem. I have a tennis ball, and the tennis ball may have two colors, blue or red. Okay, I said I will send you to both of you this ball, and this ball is the color of this ball is red or blue. So, is there any way to for you any classical device, any measurement possible in such a way that you can say by sure, yes, it's red, or yes, it's blue? Yes, of course. You take your eyes, in this case, you will measure, but another, let me say, another device, a spectrography, also on. And you can say by certainty, 100%, that the tennis ball is red or blue. The same for Alice, okay? This is not true in quantum mechanics. This is the crucial point, really puzzling. So, we will see that tomorrow, that if Alice and Bob, now, I have a photon, I have an electron, let me say, and I say, oh, Alice, I will prepare this object in this state, and I give you the mathematical description of the state. Okay, the physical system will be this, and the same to you. Then I send you the photon, and I ask you, can you say whether the spin is up or down? In which the state? I send the object in this state, in two states. It's row 1 or row 2, the analog of red and blue. I say, is this electron in the state red or in the state blue? Quantum mechanics says there is no possibility to detect 100% whether the state is red or blue, even though you know exactly the mathematical description of the two states. So, and this is, and the description, the idea of our classifier is that the better, but we will see there is an optimal way. It's not perfect, because it's impossible, at least the two states are orthogonal, but if they are not orthogonal, there is no way to guess with probability 1 in which state. There is an optimal discrimination, and this will be the base, the ground for the classification of. So the philosophy is the following: the idea. If you are able to discriminate the quantum centroids very well, from a physical point of view, you are able to classify with a high accuracy. The more distinguishable are the quantum object, the better the classification, and which is quite intuitive. And so I think I'm just finished. let me see whether I can finish with the classical example tomorrow. So I try to reduce a mathematical apparatus in such a way that it is understandable for everybody. But I see here whether it's possible to show you the, here, environment, home, this is called Jupyter Notebook. Is a notebook of Python. You are computer science. You know very well. You know Python.
Yes.
Is there anybody know Python? Many. So that's good. So let us see here is quite ugly example of melanoma. This is a real example. This is based on more than 2,000 images of pictures of benign cells and malignant cells, melanoma. Okay? And so this is, to build a classifier with which can accurately. I use the nearest mean centroid, so the more naive classifier. Otherwise, we need 2 hours, if you use neural networks or other classical classifier. Just to give an example. So I download we try again. Otherwise, because we need many packages, because one is a Python package for quantum computing, one is for classical classifier, one is for logic, because you use also for logic. It seems it is uploading the packages. In many it's written in TensorFlow. TensorFlow, which is unfortunately, we don't have GPUs here because my computer don't have, because if with GPUs is very fast, because it's written for optimization with GPU. Now you read the data, the pictures, the pixel, and every picture now is, let me say, flattened, the pixels into vectors. They are flattened. Okay. So now 2006, so we have, 2,635 training data and 660 testing data. Okay, usually is 80-20. Okay, 80 training and 20. So now we prepare the data, we flatten the data, everything. This is the preparation. So you see an example of a benign and malignant. This is melanoma. And now I have here the classifier is the nearest centroid. So I take the prototypical benign cell and the prototypical melanoma cell, the centroid. And we test the classifier with this unseen object, and we see this is the accuracy, which is not bad for a linear classifier. You see, it's almost 70%. So it's a good accuracy for a linear classifier. Then you have this classifier, and then you can take randomly. You can take. I repeat the classification, and usually take 20 or 30 seconds. It's quite it's quite fast. So you see, quite fast. With with neural network, I stopped. I gave up because after 3 hours, nothing happened. So now I test the classifier. So this is, let me see, this is false. This is a bad answer because the predicted is benign, but the true label is malignant. So this is malignant, but it's classified as benign. So this is a mistake. Say it's 70%. So this is predicted again benign and malignant. So now it's bad. So it's a bad results. In any case, from a statistical point of view, you can test it and you obtain 70%. Usually with a neural network, you can arrive more than 90%, which is a good result. I will test in the next days with a quantum. I never tried with a quantum computers to see how it works with the quantum algorithms. So I think it's enough for today. Thank you for your attention.